Thank you. And thank you for inviting me. So exactly as Arno said, I will tell you something about Gaussian processes because we only have 1 hour. So it will be sort of a sneak peek into these things. And I guess that if you aren't familiar with them from before, you might not be an expert after this, but at least you know what they are all about, at least a bit. So my name is Arno Solin. I'm an assistant professor in machine learning at Aalto University, which is, I'm a bit lost now, but in some direction, maybe 10 kilometers from here. So there are 2 universities here in the Helsinki region, and both universities have kind of a strong twist towards like probabilistic methods and machine learning and AI. So like this is the other university, and then the other one is Aalto University. Great. It was actually a good choice of words that Arto used when he introduced the topic, because now, like during this week, you have been exposed to many different types of machine learning methods and like probabilistic tools in AI. And I think the keyword there is tool, because what you're building up as students or postdocs or senior researchers when you attend things like this is that you try to find more tools for your toolbox. And I like to see like these methods as just sort of things that you collect, you put in your bag or in your toolbox. And then when you have a practical problem or you develop some great new stuff, then you need to like choose the right tools and then like use those in a creative way. So you should look at these things, not only on this lecture, but also on the other ones as sort of like things that you put in the toolbox. And they are not sort of like isolated things that only like work on their own, but be creative, like combine things, come up with new ideas. So consider this lecture kind of a additional tool, be that a hammer or a screwdriver or something else that you put in your personal toolbox. With that said, 1 hour is not a very long introduction to anything. So, and it's maybe a good question whether sort of like your 1 hour would be better spent reading a book on GPs or watching some like really good online videos. There's plenty of like recorded tutorials and lectures on GPs, but I try to give you a quick overview on different things, and then if you're interested, then you can dig deeper. Then I have some pointers in the end of the presentation. So we have roughly 1 hour, and I boldly split this thing into 4. So part 1 is like a pragmatic introduction to Gaussian processes. This is kind of the part where you have the usual sausage plots and so on. Part 2 is kind of like ruining part 1, because I talk about all the problems or the challenges that sort of like kind of break the beauty. Because like, let's be frank, I think Gaussian processes are really beautiful. It's a beautiful construction, beautiful machine learning paradigm, but it has its limitations. And those we go into in part 2. That's the snake in the paradise. Part 3 is about then like giving you some connections and like different approaches to GPs. I guess we start to be a bit out of time at this point, so I suppose it will be a bit rushed. Prepare for that. And part 4 is then like a recap, and then some pointers to further material, and then hopefully we have the opportunity to like interact in part 4. I believe that I will spend probably 40 minutes on part 1 and then rush through the rest, and there will be 1 minute for the questions. But I'll be attending the dinner, so please come and ask me there. So good. So Gaussian processes, as I said, is kind of a core part of probabilistic machine learning. At least I think like that. And kind of a bit of a personal view into machine learning. This is something that I give on like very basic courses in machine learning. Try to like students who have no background whatsoever in machine learning. And you're kind of the opposite. So feel free to disagree. But one way of looking at machine learning is to think that, well, you learn from something. There's probably some observations or data present. You have some model. You have some prior assumptions, what is generating the data. And then you need to kind of put these two parts together. And I call that algorithms. But that's kind of the glue that makes the magic happen. Be that then like inference methods, learning methods, and so on. And Gaussian processes now, well, data plays a role there. But maybe the interest there is in kind of the model part, because Gaussian processes provide a very nice framework for like injecting prior knowledge, and it's in a very explicit way. So you inject prior knowledge about what is generating the data, or what you think is generating it. And then many of the sort of like researchy parts of GPs are then related to like algorithms, how to do efficient learning and inference with GPs, because the framework itself is kind of like self-contained, beautiful. It's just like meeting all the challenges and like sorting those out that maybe bring you to the researchy open questions. So that's why most GP research is often in sort of the algorithmic part, because the models and data on the other hand are kind of well defined in the first place. And what do I mean by well defined? So now is the part where like there are like boring looking slides with some equations, and I realize that you have started at 9 today. Is so? Please nod. Yeah. So it starts to be a bit late, but bear with me. So you all know, hopefully, what a multivariate Gaussian distribution is like. And now if we try to define a GP, so a Gaussian process is a collection of random variables over a space, some input space, such that any finite subset of them have a joint Gaussian distribution. Great. Now I've told you what a GP is. But maybe we could try to put this in some more like concrete terms. So you could see GPs as like defining a distribution over functions. So if you think of a multivariate Gaussian, it basically defines a distribution over some like multivariate, like you could think like vector valued variables. But then if you keep adding elements to the vector and kind of like reach like a continuum, so that you don't have discrete things, but you actually have like something continuous. Continuous things are called functions. So a GP is a way to define a probability distribution over functions. And this is something quite profound. So it's basically kind of Gaussian distribution over functions. This is maybe the most hand-wavy thing, like explanation of what the GP is. And you know, like Gaussians are characterized by a mean and a covariance. So Gaussian processes are fully characterized by a mean function and a covariance function. So basically now what this slide says is that we have some f, which is function, that follows a Gaussian distribution, which has a mean function mu and a covariance function kappa. Okay, still quite abstract. There will be pictures and examples later on, don't worry. So now the probability of any subset, you remember like the GP was defined such that any finite subset, when you evaluate the function at any collection of points, like that like evaluated thing follows a Gaussian. So now you can choose like any inputs like x1, x2, x3, x4, and so on. And then you evaluate your function at those points and like stack those in a vector. And then you evaluate your mean function and covariance function to get like a mean vector and the covariance matrix. I call it gram matrices, which is then here. So basically the elements in K are evaluated from the covariance function. And that sort of like finite thing evaluated from the infinite, like continuous thing, and then follows a Gaussian. So you could say that like a GP. So they kind of describe like what happens for like infinitely many variables, because you can choose like any number of like inputs that you evaluate the thing on. So it's really like a continuous thing. And this kind of like also gives rise to the thing that people call GPs like non-parametric models, which kind of like would indicate that they have no parameters. But rather than that, they kind of have like infinitely many parameters, or actually like the data spans the number of parameters in the model. So they are like non-parametric in that sense. So, okay, so now like you have GPs. Now what do you do with them then? So quite often, Gaussian processes are used for encoding prior knowledge about something. Typically some latent functions that would be generating the data that you're interested in. And in machine learning, the dominant view into Gaussian processes, I stress it that this isn't the only view into Gaussian processes, and we'll go into that a bit later on. But in machine learning, people tend to favor sort of this like kernel representation, where kind of the covariance function is kind of the king. So like you take the covariance function, and that kind of encodes your assumptions and knowledge about the process, like your prior beliefs. And okay, prior knowledge. So typically that means in practice that you choose a family of covariance functions. You might have like sum up different covariance functions or different families of covariance functions, or take products of them to create something more complicated. But they are like, this is kind of the cookbooky part. So you have certain families of covariance functions that encode certain things into your problem. For example, you might want to assume that the model functions are continuous, or they are once or twice or so on differentiable, like smooth. Or then you might want to assume that they are non-differentiable or something. Or you might want to encode that you know that the thing that is happening is periodic or almost periodic. Think of modeling daily temperature. There's probably some sort of like daily or yearly variation, even though you don't know what that variation is, but you can assume that there is something like happening with like a daily period kind of in the model. Then you can learn what that is, but you like encode the assumption that there's something going on. Or then you might want to encode certain types of like invariances, like translation invariance or something else. And well, this is a bit boring, but I only like show you now here like the parametric form of one covariance function, like one kernel. And this is the RBF kernel, which is like, I don't really like the RBF kernel, quite frankly. We can go into that like separately, but so it's a really boring looking thing. Here, like the equation I had just plotted what it looks like in the range from -3 to 3. When the input is now sort of the difference between the inputs, like the norm of the two points that I give it. Why I can write it in this form is because it's a stationary covariance function, so it's translation invariant, and it's also isotropic. So it really just depends on the distance between the two inputs. And what this, like, if you look at the curve, it actually tells quite a lot. So it actually tells that the model functions are infinitely smooth, like there exist an infinitely many derivatives of the model functions, and also the two parameters of this kernel, like it's maybe not that visible, but they are in blue here. So this parameter here and this parameter here characterize what kind of behavior is to be expected by the model functions. So this, this parameter here kind of tells about the magnitude of the model functions, like how much how far up and down they go. And then this second parameter here tells about the characteristic length scale, how quickly that happens. But still, they are still like all like continuous, infinitely many times differentiable, but then like how fast they vary and how big the magnitude is can be controlled by these parameters. And these are typically then like, they are like higher level parameters, like hyperparameters. So they are then quite frankly, quite often then just like you optimize with respect to marginal likelihood and find a point estimates for these values. Okay, but there are a lot of like covariance functions. Some examples here. These are like random draws from the covariance functions. Like the kind of more boring ones, I mean, like the constant covariance function. You assume that the data is generated by kind of a constant process, just like the baseline varies. Or then like you can even write a linear model in terms of a GP. Or then you can do something more exotic, like the Wiener process covariance function. That's like non-stationary, but quite kind of practical. Or then there's all these here are like stationary covariance functions. They kind of like assume that things are like translation invariant in the prior, and they're just like basically encoding various types of like smoothness properties here. Or then I mentioned periodic covariance functions, or then almost periodic covariance functions, or then you can even like assume that the data generating functions are white noise. But these are just examples. You can basically come up with like infinitely many different like covariance functions and like combine these by sums and product, because those are also then like valid covariance functions. So they are ways of encoding what you assume that is happening when sort of the data is generated. And say, for example, if you have a problem where you want to model, for example, like the number of babies born in the US. This is an actual example that is actually on the cover of the Bayesian data analysis book by Andrew Gelman and co-authors. So there they have a very complicated prior, because they want to like model like a yearly variation that can change over time. They have like a weekday component that changes over time. Then they have like a slowly moving trend over like decades, and then they have faster moving trends over some years, and then they have like a special treatment for like holidays, like special days and holidays in the US. So it's a very complicated prior, but it all makes sense because they're all kind of like informed choices for what is affecting the data generating process. Great. So now I talked to you about like GP priors and what they sort of represent. So if we then look at the standard like GP model in machine learning, it typically takes this form. So you have the GP prior, which is pretty much what we looked into just now. I have a typo here. This should be an X, but anyway. So the prior kind of is encoding what you think is sort of like behind the functions that generate your data. And then you have a likelihood that then combines your latent functions that you put your GP prior on with the actual observations that you have. The observations Y here. And now I assume that the observation factor, so it's like a product. And now the easiest thing would be to think that, well, you just observe directly the latent functions, probably plus some Gaussian noise. And this would be like the vanilla GP regression task. But then your likelihood could be something else. You could have a classification problem where you have like a Bernoulli type of likelihood. Or then you could have like a Poisson type of model where you observe some counts. And then you need to think of like additional assumption. What is link functions that link the latent functions with then the likelihood model and so on. But this kind of a rabbit hole to go down into right here. But then you basically have your GP prior, and then you have the model that sort of couples your latent functions with your observations. This is the typical anatomy of a GP model. And now let's look at an example of this. So I tried to have at least one self-contained example. So if you now sit down after this and just write down the equations in your Python notebooks or Julia or whatever you're using, then you should get something running. But let's not dig too deep into this. It's more for your for reference. So we have a GP regression problem here, where we have been given some data, some input-output pairs, some x's and y's, so inputs and then observed outputs of something. Then we have our GP prior here. Again, have a typo here. So we assume that the GP is zero mean. You can basically always contain the mean function as part of the covariance function. So without loss of generality, we consider zero mean GPs from now on. And then we should probably have something we should probably know where the data comes from. And if we don't know, then we probably have some quite conservative guesses, or then we're just lazy and using RBF. And let's start by being a bit lazy, but I have various GP priors then to show you here. And then the observation model, the likelihood model, is now that we observe the y's, which are just directly the f's evaluated at the input points plus some Gaussian noise. And the posterior mean and marginal variance for some unseen, new test input point is actually available in closed form for this GP regression task, where the likelihood is Gaussian. And the hyperparameters of the covariance function and the measurement noise scale are often learned by maximizing with respect to the log marginal likelihood, which is also available in closed form for this. The tricky part here is that if you look at this, there is this inversion here. So the k here needs to be evaluated at all the n data points. So this is an n by n matrix, which then need to be inverted. That's the source of something interesting. And then just for reference, how to get this closed form solution, a quick walkthrough would be to write down the joint model, then marginalize over the f's, and then compute the conditional distribution for the unseen test point given the data. And because everything is Gaussian now, remember the Gaussian process is Gaussian because you evaluate it at the observations here. So it kind of collapses to the multivariate Gaussian. And then your observation model is also Gaussian. So then everything is conjugate and you can actually work out the details out of the box. So now this is the data. This is the input-output pairs that we are given. And then if we choose a typical choice for the GP prior, we can then solve the GP inference problem. I optimized the hyperparameters here first. And then we can draw random samples from the GP posterior, which would kind of represent samples that could be the data generating process. Or then to actually see something more, we can keep sampling posterior samples and see that what happens here. And now you see that, well, they fit quite well here where there's data constrains them, but they're in this part where we basically extrapolate, they start to spread more. But because the covariance function, the prior assumption that we encoded here, in this case is that this is a Matern 3-2 model, which basically encodes continuity, some differentiability, and mean reversion outside the data, because it's stationary. GP prior. So then what happens here outside, that it tries to revert back to like the 0 level here. So that's why they don't sort of like escape. And we can keep sampling these functions, and that sort of characterizes like what the prediction is. But quite often, this is presented in some other form. You can also just evaluate the kind of the density, or then plot some like intervals. So now the blue line is the GP mean, and then the dashed lines are the 95% like credible interval for this. And this is how they often like present these things. If we choose some other type of prior, because now like if we are just given this data, we don't really know what is generating it and what should happen outside the data. We can probably just by looking at the data say that, well, it's probably something quite continuous because it sort of follows like this. But what should happen outside? That we don't know. And this is now like a Wiener like integrated like Wiener model prior, like a Wiener velocity model, which basically encodes the assumption that outside the data, it kind of like continues in the direction of the derivative close to the border, which might be a sensible choice or then not, because, well, if we would have some additional information, we could encode that in the prior. So now you see that actually the choice of prior affects a lot what happens, because if we have informed thoughts of what is generated in data, we can now sort of put in that information here. And that would then be sort of like you see the GP mean shoots off there. And this is an equally good model because we don't really know. But if we would know that sort of like this is what should happen. And if this would, for example, be, we would be modeling a car tracking example, then probably a sensible first choice would be that the driver just lets go of the wheel and continues in the same direction that they are going. So in that sort of like tracking examples, this sort of non-stationary priors are actually really good. Or then, if we would happen to know that there's something periodic going on, we could use a periodic prior, and that would give us something like this, which is, of course, it's a kind of strong assumption, but it also strongly sort of like constrains what is happening. And now sort of the 95% interval is smaller because sort of like it's sort of like you're using more stronger prior knowledge on what is happening. Now you see the role of the prior assumptions are actually quite important. And in this case, quite frankly, I generated the data set a long time ago, and I already forgotten what was actually generating the data. So I don't really know anymore. But it seems to like all these three choices that we had were actually kind of sensible. So like if we would have some more information, if this would be sort of the daily temperature or something like that, then we should probably go with the periodic model. Great. Okay, that was a very quick and shallow introduction to GPs with kind of a twist towards GP regression. So GPs are actually quite beautiful objects, and now like the examples were super simple, but you can do a lot with GPs. But there are challenges, and yeah, typically the first challenge that people sort of like come up with or mention is that, well, there's that matrix inversion, and it, like you need to calculate determinants and stuff. So you need to invert a big matrix. Of course, you don't explicitly invert things when you implement it, but it's like solving a big linear system. And that scales cubically with the number of data points. And now that basically means that when your data grows 10-fold, your compute grows like 1,000-fold. And even though computers are fast nowadays, they are not that fast. So still like inverting a matrix larger than 10,000 times 10,000 start to be a bit heavy. So that is kind of a limitation. So like having like millions of data points in a naive GP implementation is not something nice. The second problem that, not a problem. Second feature, thing, challenge, what we should call it. I use these skulls here, but it's nothing like fatal going on here. It's like dealing with non-conjugate likelihoods. So now in the case of GP regression, we had a Gaussian observation model. We observed the latent functions plus some Gaussian noise. And that is super nice because then you have like everything is Gaussian and everything just falls out by pen and paper. So you can solve everything exactly, which is of course super beautiful. But often you don't have a problem like that. You want to do classification or something else. So then you need to do some choices. And the third thing is that the representational power is kind of limited. So GPs are great, and in theory, you can use them for anything. But there are certain applications that they're better suited for than others. And for example, computer vision is maybe not something that where you should look in your toolbox and first take out the GP tool. Of course, when GPs can play a role as part of bigger models, but especially if you do large scale image classification, then maybe if you start off with GPs, you're maybe off. So what can you do? Well, this is also like a rabbit hole. But actually turns out that I think it's rarely a real problem to deal with large data sets, because you can exploit so many different things, and actually tools nowadays, they are quite good at sort of helping you out, even though you wouldn't be kind of an expert on the topic. So what you can do is that you exploit different things. You either exploit the structure in the data. In case your data is in a grid, you're super lucky. Things are very easy. Or if your inputs are in 1D, you have a time series model, you're super lucky. Things you can do immensely efficient things. Or you can exploit structure in the GP prior. So if your GP prior is stationary, there's a ton of methods that basically leverage the connection to spectral methods and so on, Fourier transforms and stuff, because then you can represent the same problem in Fourier space and so on. But stationary priors, you're lucky again. And actually, in many GP models, people restrict their interest to stationary models. Or if your GP prior is separable over input dimensions, that also helps, and so on. Then there's been work that, well, let's tackle the solving of that big linear system. You can do a lot of standard tricks that are developed elsewhere and used in all other fields of numerical methods and mathematics. You can, for example, use conjugate gradient solvers for the inversion. So and that tends to work quite well in many cases. You can also then exploit things you kind of split your problem into smaller chunks, having kind of a committee of expert kind of things that you have one model that looks at this region in the input domain, and another model that looks at this region, and so on. Or then you do a subset of data. There's a lot of choices here. You can also then approximate the problem itself. So you have a low rank approximation to the GP structure, or you use inducing points for projecting down to the model to some points. These are related to so-called Newstrom methods. There are a lot of papers about this 20 years ago. Time flies. Or then you can approximate the problem solution. And this is maybe the dominant view for plug and play inference nowadays. There's these sparse and stochastic variational methods, which tend to work decently enough for many large problems then in the end. Okay, so it's actually not that bad if you have a lot of data. It's kind of a happy thing. The other thing that I mentioned, the second skull, was dealing with non-conjugate likelihood models. And well, there you have the standard set of tools that we have in probabilistic ML, many of which you have been sort of like discussing or covering in other contexts already, even this week. So of course you can do like actual inference due to sample, which can work great. There's a lot of like good sampling methods, good tools for this, and you typically end up with good results. And sometimes these are heavy, but then you get good results. Or then you can use something super lightweight, for example, the Laplace approximation, where you basically find some point estimate. You like use a Newton method or something to find a point estimate, and then you evaluate the Hessian around that area to like look at the local curvature, and then take the inverse of that for your like Gaussian approximation to the problem. This is fast, very simple, and it's a bit embarrassing, but it actually turns out to work like decently well in many like simple problems, but not in all. So maybe not the first choice nowadays, and I think not even many of the like standard software toolboxes even implement the Laplace approximation. Then there's something called the expectation propagation, where you basically kind of like find you restrict your interest that it should be Gaussian, and iterate there as well. It's more like complicated to cover. Let's just say that it tends to work quite well, efficient, but it has its own tricky parts. No guaranteed convergence in the general case, and implementation kind of typically requires a lot of tuning per model. That's why maybe the dominant method nowadays is like variational methods, which are kind of provides nice plug and play type methods, but are certainly not problem free, and also then tend to kind of like be mode seeking, kind of like overestimate variance, and a lot of like these kind of small details, but maybe a good starting point for many things. That's super shallow, but anyway, now you at least heard that these methods exist. And the third problem point that I gave you was that GPs are maybe not the right tool of choice for every possible thing. It hurts my heart to say this, but it's maybe true. So GPs can be seen as shallow models, not deep, but shallow, but infinitely wide. And we'll come into why this is the case just in the next slide, actually. And thus they might not be ideal for problems where the data resides on some like low dimensional, complicated manifold in some like very high dimensional space. Read that as images. Because images typically they have like a very high dimensional space where actually the manifold of any sensible image that represents anything that a human would understand is actually like a tiny manifold there somewhere in that space. And then like for GP to kind of like learn that correlation structure, like you need a lot of like clever tuning and tinkering to do that. And I'm not saying that you cannot do it. It's just not, but it's maybe not the first choice. But on the other hand, GPs can be great tools then to combine with your fancy like neural network model or something else, so that they can play an important role in like a bigger system for then like encoding knowledge to some part of the problem, or then help with quantifying uncertainty or something like that. Great. With that said, exactly as I thought. Yeah, now is the part where I rush through a couple of like connections and approaches to GPs. We have plenty of time still, don't worry. So I told you that GPs can be seen as shallow, and infinitely wide. And there's a nice and actually kind of peculiar connection to neural networks here. And this is not a new thing. Yeah. Even though like people tend to think that everything was like invented in the past 4 years, but this is definitely not a new thing. And actually a thing that people were looking into quite in detail in the 90s, before any of these things that we talk about in this summer school were cool, or existed in the current form at least. So you can think of a single hidden layer, feed-forward neural network, and then if you just keep adding nodes to your hidden layer there, and you take the number of nodes to infinity, you basically get the GP. And this is actually a quite interesting connection. And if you're interested in these things, I recommend to read. There's a chain of papers since the 90s on this, and there's a lot of like interesting stuff there. Now I regret not including some more figures about this. But you can actually like evaluate what the covariance couples kind of the role of the choice of the architecture and activation functions in a neural network to what prior it's encoding over the kind of model functions. And this gives sort of tools for analyzing, understanding why neural networks with certain activation functions behave in certain ways. And you can actually take the limit, then you can take a ReLU or something like that, and then actually calculate what sort of that infinitely wide ReLU network actually induces in terms of a GP covariance function. And it's actually super interesting. I think so. So I recommend that you look into that if you have a spare time. Then we enter something that is super sort of like important for me, because this is something that I worked on during my PhD. So I worked a lot on connections between Gaussian processes and then like signal processing methods and stochastic differential equations. So how to convert GPs in one representation form to another, either to leverage some existing theory on sort of like signal processing, or then being able to convert, for example, like first principles models in signal processing to GP priors and so on. So I talked about the moment representation, basically the way of representing the GP prior in terms of a covariance function, a kernel. And that is convenient because then you stack all your knowledge into that sort of like kernel function. But you can also then have kind of equally expressive representations in other forms. For example, in terms of like a spectral density or a state space model. In continuous time, that would be a stochastic differential equation. And you can represent kind of the same prior in these different forms and like move back and forth between the representations. And why is this relevant? So if you have a one-dimensional GP and you convert that to the state space form, you can actually leverage methods for signal processing, say Kalman filtering, for doing the exact GP inference in linear time. And now you remember it was cubic in the standard case. So if you go linear, you can actually do like big data sets. So this just visualizes what it means to be linear time. So you actually like consider one data point at a time, like in a forward sweep and then a backward sweep. And this actually recovers exactly the same solution as I showed you earlier, where we actually inverted the big matrix. So it's beneficial to think of connections between different fields of mathematics or machine learning or so on, because that can sort of like give you a new sets of tools. There's also a lot of connection to physics. Why? For several reasons. Often in physics, you represent your knowledge about problems as differential equations, be that those then ordinary differential equations, or stochastic differential equations, or partial differential equations, or stochastic partial differential equations. But anyway, differential equations model change. And GPs can often be used as like structure priors, kind of like model like latent forces, kind of invisible hands that move things around, or for quantifying uncertainty in these models. And why they're so handy for this is also then like if you think of like linear operators, like if you study any physics, you know that linear operators are everywhere. So GPs are actually sort of like closed under linear operations. So if you have a GP and you apply a linear operator on that, the resulting thing is still a GP. It just has a different like covariance structure. So that sort of like gives rise to a lot of like interesting stuff. And then I cannot skip Bayesian optimization because I think BO made GPs cool in a different way some years back. So if you're not familiar with Bayesian optimization, like the basic idea is that if your optimization problem is such that it's super expensive for you to observe things, to evaluate the target function, say that you're drilling oil and you need to drill holes to check whether there's oil or not. So then one hole can be super expensive to drill. So then if you can choose more precisely or better the next place to drill at, then that can be very important. So let's say this problem here that you have now observed the your function at 3 different points, and then you have some like prior knowledge about that it's maybe continuous and maybe differentiable and so on. So then the question is that where should you evaluate the function next? The blue patch tells about your uncertainty about things. So then the acquisition function here tells about like expected improvement. And then if you try to maximize that, you choose the highest point. That should give you the next sensible place to observe at in order to find the maximum of that hidden target function. That was a super quick introduction to BO. I'm proud of this figure because I implemented this method in the morning just for you on these slides. Great, we have 10 minutes left. The other thing that I did in the morning was that I dug up some toys under the bed of one of my children, and then took a photo of them just as I could include it here. So this has been like a shallow but quite wide introduction to GPs. And if you should remember something from this, is that Gaussian processes provide a plug-and-play framework for probabilistic inference and learning. And what do I mean by plug-and-play? It's a well-defined construction. It's not something that you need to tinker with, because it's there, it's beautiful, and it always works. So you can take this framework and just put your problem there. The actual problems are then that if you have a lot of data, or if you have a non-conjugate likelihood, how do you actually then solve the problem? But at least you can formulate the problem like out of the box. So it's a plug-and-play framework. And if you can solve the problem, if you have the tools then to run things, it's more like pressing a button and hope for the best. They give a very explicit way of injecting prior knowledge into a problem. You can really sort of like see where are your assumptions and like how they affect things. And they provide meaningful uncertainty estimates and means for quantifying what the model is uncertain about. They are beautiful. If you want to like go back to basics and like start your journey into actually like working with GPs, understanding them in a more deep fashion, I recommend this book. This like it's not that old, but a book published in 2006 starts to be like a long time ago if you think of what's happened in the past years now. But this book is still good. It's still like it has kind of a lot of the essential things, and it's available online as well. If you want to see more of me explaining things, then I recommend that you watch my ICML 2020 tutorial on signal processing methods for GPs and SDs and so on. Shameless self-promotion. And if you actually want to just dig in and start using these things, there are a lot of quite nice tools available. So the ones on the top are for Python. There's all sorts of Julia packages, but I don't know how far they are yet. But GPFlow uses TensorFlow, GPyTorch uses PyTorch, GPy uses Python. It's an older package before the time of these more fancier frameworks. And then I included 2 additional ones in gray because they are in MATLAB. And I know that MATLAB is not something that people use nowadays, but the fact is that a lot of sort of like very well derived and very much researchy stuff have not been ported to these newer packages because they are available in other packages, like in MATLAB. So if you actually do research on these things, you should probably keep looking or even older things than just 4-year-old things. A lot of good stuff happened like before. What else? There is a Gaussian process summer school, which runs typically yearly, and it's usually in Sheffield, and it's in Sheffield this September, and it's an actual like in-person event, and it's a really good summer school, like probably as good as this one, I would say. So if you're interested, I think you can register for this already now. That was the last slide. We have 5 minutes for questions, and I'm opening the floor for questions now. Please, you. It needs to be a covariance matrix because the covariance function needs to be a positive semi-definite function. So then by definition, it's always a PSD matrix. So it's always inverted. That's the quick answer. Yeah. First here and then there. Yeah. That's a good question. Just to correct, not infinitely deep, but infinitely wide. Yeah, but still. There might be better comments on that. Maybe I think we have like a BNN lectures on Friday. But I personally find it that it's a great tool for analyzing what is actually happening, because I think we all kind of agree on that it's not always easy to interpret what the inductive biases are that you kind of like implicitly encode into your deep model by choosing like an architecture and activation functions and so on. So I see this link as a tool for understanding that what sort of the kind of like inductive biases are that like the neural network might encode into the problem. Bad answer, but maybe that gave you some pointers. There was a question there somewhere in the back. Yeah, good point. I think you all heard that because I heard you and you're in the middle of the room. So yeah. Yeah, because true. People online might not have heard that. So the question or comment was that there is work on actually sort of interpreting parts of the neural network, typically like the last layer as a Gaussian process. And that's actually is it's a very interesting thing. And this kind of relates to what I said, that GPs might play a role as building blocks of like a bigger thing. So then you could interpret that your first layers are kind of taking care of extracting some interesting features, and then you kind of do GP inference on those features that you have extracted then on the last layer. And this actually tends to work surprisingly well in many cases, at least to my experience. So it's a good point. There was a question somewhere here. The question was that when can you actually rewrite the GP problem in the state space form so that you can do the inference by Kalman filtering? I love this question. I'm super happy to answer it. So basically, the covariance function need to be Markovian. That is the short answer. When is it Markovian? That's more complicated. So if we go back just a bit, I actually sort of on purpose included this figure here, just to be able to answer this question. So for example, all these covariance functions have a representation in terms of a linear time invariant stochastic differential equation. It's exact for the constant, the linear, the Wiener process. All these have an exact, and the noise as well, representation in terms of an SD, which means that you can do exact inference with Kalman filtering. The squared exponential, rational quadratic, the periodic, and the quasi-periodic covariance functions, they are infinitely smooth. So you have like infinitely many derivatives that you would need to include in the SD that you have. But those you can like approximate to a very, very high precision. So actually, like this figure is taken from my PhD thesis as examples of models for which it's easy to do. So the short answer is for time series models, it's typically possible to do it. So it's not an actual like limitation in that sense. So the question was that what is the role of the hyperparameters then in the state space model, basically? And yeah, indeed. So you take your covariance function, you convert that to an equivalent state space model, and then the hyperparameters then typically they start appearing in the like the dynamical model matrices in the various places in typically quite like a structured but rather complicated manner. But for most models, there's actually like a one-to-one mapping and sort of like you can derive the connection like in closed form. So yeah, but they just become parameters of the state space model. If you're interested, please read. I think I snuck in some other shameless self-promotion here as well. Let's see if I can find it. Yeah, so we have a book that came out in 2019 by Cambridge University Press. It's called Applied Stochastic Differential Equations. And in the last chapter, there's like on this connection and also then like the form of these. And there are also there are several software toolboxes where these have now been implemented. So you don't need to reinvent the wheel, but there actually is like plug and play code that just does the transformation for you. Any more questions? There's one at least. I didn't quite get the question. Like, is there? Yeah, you can evaluate the so basically, for example, in GP regression, what you actually get out is a posterior GP, which you can evaluate at any point. But then typically for implementing on a finite memory computer, you then typically choose, I don't know, a linear grade of points that you then evaluate at so that you can draw these sausage plots. They're called sausage plots, where you basically have, I love the term, like it looks like a sausage. Look, so yeah, so then, but it's actually a continuous thing. You can evaluate it at any point. I hope that answered. Kind of. Any more questions? There's one here. Yeah, like the Markovianity is a bit tricky to define, because like now it's easy to have like a discrete state space model where you can draw those like bubbles and then you connect them by lines and then say that, yeah, this is independent of the past given that you have like the previous state. But then now in the SD, it's a continuous thing. So then kind of it's more than related to the derivatives of the process and how they interact. So that's why it's a bit abstract to talk about like Markovian kernels, because it just says that, yeah, you can write the kernel in terms of an SD. So it's kind of like, yeah, you define it by saying that, yeah, it's possible to do it. So that's why it's not very meaningful in that sense. So it's maybe easier to think of that any linear stochastic differential equation can be written out as a kernel in an easy way. And there's like a one-to-one mapping. Like, look, the book gives that as well. So how to actually evaluate that if you have a linear time invariant or even like time variant SDE, so how to convert that into the equivalent like kernel representation, various function. Yeah. This is the sign that it's time to stop. I'm handing over to Arto.